Okay, so here we are back in the molecule simulator, and I just want to run through some of these shapes with you. So of course here we have a linear, we have two central atoms, no lone pairs, and you ought to have your notes out on molecular geometry right now. And we can see that bond angle is 180 degrees, okay? Molecular geometry, electron geometry in the lower left, they are both linear. Now I'm going to put another atom on there. Again, um, as long as we don't have lone pairs, the molecular geometry and the electron geometry are going to be the same. 120-degree bond angle, these are trigonal planar. Remember, three things make a triangle where you rotate it, everything's in the same plane. Okay. Now I'm going to take one of those lone pairs off. I'm going to take an atom off, put a lone pair on there. All right. Now look at the geometries down the lower left. Molecular geometry is now bent. Electron geometry is still trigonal planar. Okay. So it has the same basic shape, but because we replaced an atom with a lone pair, we get a slightly different, or we get that different shape, which is bent. All right, take that lone pair off, and now I'm going to have four atoms. Okay, four atoms gives me the tetrahedral shape. And molecular geometry, electron geometry are the same because there are no lone pairs. And we can kind of rotate this around. It's symmetrical in every direction. All right, take off an atom, put a lone pair on there, and what do we have? Now we have trigonal pyramidal. This would be like ammonia. Okay. And if we rotate it around, all those bond angles are 109.5. Because if you watch the bond angle video, they're not exactly 109.5. They're a little bit smaller than 109.5. But here, molecular geometry and electron geometry are not the same because we've added the lone pair. Add another lone pair. Oh, get rid of one of those guys, one of those atoms. So now we have something like water, H2O. Still the basic tetrahedral electron geometry because there's four things around the central atom. Molecular geometry is now bent. Okay. And again, that bond angle is just a little bit compressed. That would be more like 104.5. Again, watch that bond angle video. Okay, so let's go to 5 things. Okay, so this is, remember, is where it gets tricky. Here is our trigonal bipyramidal. Molecular geometry, electron geometry are the same because, again, no lone pairs. We have the axial position. Those are pointing up and down, and then spinning around. Those are the equatorial positions. So axial, always 90 degrees from everything. Equatorial are 120 from each other. Okay? Equatorial and axial. Very important that you remember that. Now, I'm going to get rid of an atom, put a lone pair, and does it become axial or equatorial? It goes in equatorial. See that? We still have the axial position there. We can rotate it, and that lone pair is in an equatorial position. Now that bond angle of 120 degrees would also be a little bit compressed, a little smaller than 120 because of that lone pair. As with those 90s would be a little bit compressed as well. But notice the molecular geometry is seesaw, and the reason we get seesaw, if you think about it like this, okay, we can, I don't know if I'm going to be able to show you, but if it rotates, if it kind of pivots on those, there we go, we can make it just kind of seesaw back and forth. How about that? Pivots on those equatorial positions and the axial positions kind of rock back and forth like a seesaw. You can YouTube what a seesaw used to look like. They pinch kids' fingers, so we take them out of playgrounds. Anyway, molecular geometry and electron geometry are not the same. Molecular geometry is seesaw. Electron geometry is still trigonal bipyramidal. All right. Take another atom off, add a lone pair. That lone pair also went in to the equatorial position. So now we get the T-shaped molecular geometry, still have trigonal bipyramidal electron geometry. Okay? And again, those bond angles would be a little bit compressed from 90. They wouldn't be exactly 90 because the lone pairs take up more space. All right. Add one more lone pair, take off an atom, and now here's where we get the linear molecular geometry, and we have that trigonal bipyramidal. Now ask yourself this, would this bond angle be correct, 180 degrees? Or would it be a little bit smaller? Well, it would be exactly 180 degrees because no matter which way you turn this, 180 degrees minimizes the repulsion. Okay, on to octahedral. Remove all these lone pairs. There we go. We have the octahedral electron geometry. Every position is equivalent, does not matter which way we turn this, they're all 90 degrees from each other. Remove an atom, add a lone pair. Now we have this square pyramidal molecular geometry, and hopefully you can see that here. Okay, this thing is really funny to try to get it to rotate the way you want it. Anyway, there we go. There's this square pyramidal. Okay, a little square on the bottom with this guy up on top, the one that's wiggling. I use the tip of the pyramid. And again, molecular geometry and electron geometry are different because we have a lone pair. Okay, so let's get rid of an atom, add a lone pair. Now we have the square planar geometry. Because we want to minimize repulsion between the electrons, they go opposite each other. Okay, they have to be opposite. And it doesn't matter which way you turn this, we're going to have 90 degrees, and that is the correct bond angle because that will minimize repulsive forces because they're being pushed from both directions, the top and the bottom, if you will. And again, square planar, everything is on the same plane. All the atoms are on the same plane. All right, remove an atom, add a lone pair there. Now we have the T-shaped geometry. Okay, T-shaped geometry and octahedral electron geometry. Again, on that one, it didn't matter where we put that lone pair because they were all equivalent positions. And I guess that's it for all of those geometries.